Hi everyone, in this video we're going to discuss heat and work. Okay, as I mentioned in the previous video, heat and work are the only two modes of energy transfer. Okay, they are the only two ways we can recognize when energy is crossing the boundary of the system. Right? Now let's go to the simpler form of energy transfer, which is heat. So I think we all know what heat is. Whenever you feel a temperature that is higher than normal, then you say that it's hot. Okay, there's heat available or heat present. So again, in a closed system like this, uh, of course, it has a physical boundary, and these are the only two ways we can recognize energy transfer. Okay, heat transfer specifically happens when? Okay, I think I asked this question. What is the difference between heat and work? So the difference is heat transfer will definitely happen when the temperature of the surrounding is different from the temperature of the system. Okay, so this first example, this drink here is 25 degrees. It's the same as the temperature of the surrounding. That means there's no heat transfer. Okay, and compared to this is 15 degrees. That means you know there will be heat transfer. Maybe you don't know how much. This is what we can find out based on what we're going to learn. Not in this chapter though. Okay, but if you compare it to the last case, this is 5 degrees, even lower than the second one, there will be more heat transfer. Okay, so the amount of heat transfer depends greatly on what is the temperature difference between the two bodies, okay, or the surrounding and the system. So all these are things that you already know, except that now we're putting it in theory like this. Okay, so this is just a formal definition. The same slides are already uploaded in week 4. So if you want to look at it at your own pace, you can just download the PowerPoint slides. Okay. Now, another example. So we have a baked potato. So we know that baked potatoes are always very hot. Okay, when you order them at the restaurant, they are served very, very hot. But we will not know that it's hot if the energy just stays inside. The thermal energy stays inside. We don't know that it's hot. Only when it crosses the boundary as heat. So the same amount of thermal energy will cross the boundary as heat. Heat is what we call it. Okay, we call the level of hotness as heat. Okay, so this heat is going to come out as thermal energy. It's only recognized as heat transfer as it crosses the boundary. Okay, now the symbol for heat is this capital Q. Please write it down. I hope you're treating these videos as lectures so you can write down some notes. Alright, so the symbol for heat is capital Q. Of course, we can have small q just like everything else, which is Q divided by mass. Or this is heat per unit mass. The symbol is per kg. Notice that Q is it has the same symbol as energy, which is kilojoules. Okay, because it is a type of energy. Okay, and the rate of heat transfer can be calculated by rate being the Q with the dot. Okay, I think I've mentioned this in the previous video. A rate of anything can be written this way, and it can be calculated by taking that property, dividing it with time. Okay, so Q divided by T, you get Q dot. So if you have Q dot and you have the total time, you can just find the total heat. This whole concept applies to all properties. You're going to see it repeatedly. Okay, so some example here. Let's say you have a total heat of 30 kilojoules is being added into the system. So Q will be 30 kilojoules. The mass of the system is 2 kg, and the time it takes for this transfer to happen is 5 seconds. So from here you can find two things. What is the rate of heat transfer? Rate of heat transfer will be how much heat is transferred in the same amount of time. So 30 divided by 5, you get 6 kilojoules per second. Kilojoules per second or kilowatts. Okay, kilojoules per second will automatically give you kilowatts. You can also find the heat transfer per unit mass. How much heat transfer per kg inside the system? So we transfer 30 kilojoule for 2 kg. So per kg will be 30 divided by 2, 15 kilojoules per kg. Okay, something very special here. I need you to write this down in colored letters if possible in your notebook. The adiabatic system. The word adiabatic here you need to remember. Adiabatic process means that in this process there is no heat transfer at all. So adiabatic equals to Q equals 0. So heat transfer is not something we can help. That means it will naturally happen as long as there's a temperature difference, even though it's just 1 degree, heat transfer will happen. So in order to achieve this adiabatic system, you need to put insulation. You know what insulation is, right? So we need to put insulation to ensure that no heat transfer happens. No heat can go in or come out. All right. So that's it about heat transfer. Now we go to the other type of energy transfer, which is work. Work is, well, it's not complicated, but it is quite a lot of things. Okay, so typically work is when energy transfer is associated with distance. Okay, I think you know this when it's force moving through a distance. So it can be any type. We have here a piston. Obviously, the rising piston involves the movement of the pistons through some distance. Okay, rotating shaft, even though it's not through a linear distance, it is a rotation. Therefore, also considered as force moving through distance. And a special one will be electric wire. So electrical work is considered as a type of work too. Yeah, there's a special equation for you to calculate it, which we will see in later slides. Okay, so how to know whether the work is positive or negative? We just use in and out. Work in, that means you are pushing the piston in. That's work in. Okay, that means the force is coming from outside. It's pushing in. And work out is when the system is pushing itself out. It's in and out. So work out means the system is just rising by itself, expanding by itself. Right? So the same calculations can be done. We have a total work. So the system now, look at this arrow, it's pointing out. That means the system is doing work. It's not specified what type of work. Doesn't matter. It can be a rotating shaft maybe. Okay, the system is moving a shaft attached to it. Maybe. The mass is 2 kg. Time is time is 5 seconds. So you can still calculate the same thing that you calculated for heat. So this is W dot, which is work per time or rate of work. And this is work per unit mass, right? So this is the equation. This is work divided by time. Now, this is in kilojoule per second or kilowatt, just like all other energy terms, just like energy, just like Q. And this is also known as power. I'm sure you know this. Power is in watts or kilowatts. You've learned about it before. Okay, so sometimes the word power is used instead of rate of work. Right, so write all of this down. It's a lot of information. Now we come to electrical work. So electrical work does not really have physical movement that we can see, but we know that it's a movement of current through the circuit, right? So we know this. And the important thing that you should note down here, please write it down among all your other equations. Electrical work, E here for electrical, equals to VIT. You will need to use this equation. V is voltage. Write that down too, because you might think this V is volume or velocity, and it's not. This is voltage. Times I is current, and delta T is of course time. And we know that voltage is in volts, current is in ampere, time here is in seconds. So those units, volt times ampere times second, will automatically give you the unit of joules. Okay, and of course we can divide it by 1000 because we always use kilojoules here, right? Now let's look at the mechanical forms of work, the actual moving work. So there are two requirements for work interaction to happen. There has to be a force acting on the boundary, and there has to be movement by the boundary. So the very simple example of work is when you're pushing something. The force is coming from you, and the movement is coming out from the object that is moving. It's not moving randomly, it's moving where you apply the force, right? Okay, so simple representation, the force is moving through the distance S to this position. You know this equation. Again, please get comfortable with the units. If you are not clear, you can ask yourself, why is the unit joule? Why work has the same unit as energy? Okay, please ask all the why questions. When force is not constant, we don't really use this, but in a case where force is not constant, sometimes it's fluctuating. So we need to do the integration of force with respect to the distance to find the total work done. Because if, let's say, the force drops to 0, then at that moment, there's no work. Okay. Now, very simple cartoon here to understand work. If there is no movement, there is absolutely no work done, even though the system may contain a lot of energy. Okay, no work done at all. Now, let's look at shaft work. It's simply the rotation of shaft. You've learned about torque in other subjects. Okay, I'm not going to go too deep into this. Again, you can download the slide and go through it if you want to. We write shaft work as WSH to represent shaft. If you have to calculate it, this is the equation. 2 pi revolution times torque. Torque is simply force times radius of rotation. Very simple. And then power, of course, is work divided by time. So this whole equation divided by time. Which part you can divide with time? Of course, the revolution. Okay, that's the speed, the angular speed, right? N over T. So shaft work is very common in engineering practice. Okay, because it involves, engines will involve shaft work. Alright, and here it says that shaft work is proportional to the torque. Torque is here coming from the force. Higher force, higher rotation. Next, we're going to look at spring work. If you're tired, you can pause the video. I'm just going to continue. Spring work, I think you've seen this equation, Fx. Alright, spring work, W spring equals to F times change in the displacement. And F is coming from Kx. K is the spring constant. You've heard of the spring constant before. Okay, so example, a linear spring will have a linear displacement according to the magnitude of force. If you double the force, the displacement will be double. That's all. Okay, so what you need to write down is that the work of a spring is given by this equation. It's half kx squared. Alright, please write it down. It's half kx squared. X here being the initial and final displacement, for example, in this case. Initially, it's at 1 mm displacement, finally it's at 2 mm, so this is what we put in the equation to find the total work done by the spring. Okay, so we reach this example. Determine the power required to accelerate a 900 kg car from rest to velocity of 80 kilometers per hour in 20 seconds on a level road. Very simple experiment. The car is 900 kg. You want it to move from 0 or from rest, not moving, to 80 kilometers per hour. This is not that fast. Okay, this is the speed limit on federal highway. And you need to take only 20, not only 20 seconds, you need to take a long time, 20 seconds to achieve this. So how much power is required? A level road simply means a flat road. So the equation for power, the simplest equation, general one, power is simply work divided by time. Okay, let's just assume we don't know yet what is this work. So we just use this general equation. Work divided by time. Do you know the time? Yes, it's 20 seconds. Do you know the work? This is what we have to find out. Okay, the work is depending on what process is happening. So the process now is that the car is moving from 0 velocity to 80 kilometers per hour. So notice that the movement here is related to the velocity of the car. The car is speeding up. What energy is that which involves velocity? Okay, I hope you recall it's kinetic energy involving velocity. So the equation for KE, you've seen it in the previous video, is half mv squared. Okay, so we put all those in the equation. This time we have change of velocity from 0 to 80. So we have v2 minus v1 always. So you write it this way. v2 squared minus v1 squared. Okay, so half times mass times v2 squared minus v1 squared. Why? Why you have to divide by 3600? Because to change from kilometers per hour to meters per second. Remember, in this equation, we always use the standard units. So change from meters per second, this is v2 squared minus v1 squared is of course 0 because v1 is rest. And we still have to divide by 1000. Why? Because the whole equation here, half mv squared, if you use the standard units, the answer will be in joules. I've said this before. So to get it in kilojoules, which is what we like to use, we divide it by 1000. As simple as that. So this is the work. So the power is then work divided by time. Simply substitute the values. You get this answer. Okay, so we're going to stop here for this video. There will be two more slides that I'm going to discuss with you in our virtual class. Alright, so rewind this video if you have to. It's a very long video. You can pause and I'll see you in the virtual class on Monday. Bye.